What if I told you you could build your own media server using nothing but free software that's more flexible than commercial solutions, supports mismatched drive sizes, and grows with your needs? Well, in this series, I'm going to show you how to do exactly that. Choosing how to store your data is one of the most hotly debated topics amongst data hoarders. In fact, I frequently find myself discussing this topic with friends, my poor family, and anybody else who will listen. Back in 2016, I wrote a post over at linuxserver.io entitled The Perfect Media Server. This video is a long overdue discussion of those ideas and principles. More recently, I converted that blog post and the ones that came after it into a documentation website you can find at perfectmediaserver.com. In this multi-part series, we're going to dive deep into setting up your own media server, and we'll do this using nothing but free and open source software, namely Linux, mergerfs, SnapRAID, and Docker. In this part one of what is going to be a multi-part video series, we'll discuss the tools and why I selected them. Part 2 will come in a week or two, and in that, I'm going to walk you through the process of taking a bunch of random hardware bits and putting them together into a functional system. So part 2 will be the hardware video, and part 3 is going to be the install and configure this thing type phase, followed by part 4, which will come soon after, where I'll start looking at like top 10 self-hosted app lists that you can install things from, like the one I have over at perfectmediaserver.com. Of all the things I've ever done in my, well, I don't want to say my life, but it's kind of true, building a DIY NAS around these technologies has actually been a true labor of love, and I am pouring a decade plus of experience and testing into this series. Not to say that there aren't other perfectly valid approaches to building a media server, but many of these recommendations earned many of these grey hairs in my beard, and they are the result of hard-fought late-night battles before we had AI to dig us out of any holes. It's a collection of tools and techniques and philosophies about building a perfect media server, as opposed to this is the way you must do it. Now, before we get caught up too much in the tooling itself, though, let's just take a few moments to think about what we want this thing to be able to do when we're done with it. So, first of all, I wanted to act as a network-attached storage, so a NAS and NAS, to serve files across the network. I also want to be able to group multiple hard drives under one pool or mount point, and each disk should be its own individually standalone mountable thing, no striping. It should also be flexible and upgradable over time and support hard drives of mismatched sizes, as well as not require a large upfront investment of 10 identical hard drives. For me, adding 1 to 2 drives a year is quite easily achieved, either as replacements or additions. Now, I also want this to have some kind of fault tolerance for failed hard drives, because these little guys are out to get you. Make no mistake, they will fail. It's not a matter of if, but when. I also want file level checksumming to guard against bit rot. I also wanted to be able to saturate a gigabit LAN connection for both reads and writes. On top of all that, I want it to run on commodity consumer grade hardware. You know, this isn't an expensive Dell box, for example. This is just a random motherboard, a random power supply, commodity hardware that you can buy used off Facebook Marketplace or eBay, or even buy it brand new if you want to. Once we've got the hardware taken care of, I want to be able to run a suite of self-hosted applications like Jellyfin and Image to do photo processing. If it can do a little bit of local AI too, maybe that would be fun. But perhaps most importantly, this needs to be using free and open sourced software, and I don't really want to be having to worry about subscriptions or licenses or rug pulls happening down the road. I want to build this solution once and have it last a lifetime. Let's start by giving you a quick overview of the building blocks we'll be using to put this thing together. First up is mergerfs. This is the layer that sits on top of your data disks, and it provides a single mount point for your applications to read from and write to. It's not a file system per se. Despite the name, it merges other file systems transparently together for you instead of being a file system in and of itself. Next up is SnapRAID. Now, if we're using something like Unraid or ZFS, fault tolerance is built in as part of the design of the system, and we get that for free out of the box. But with mergerfs providing no fault tolerance, we have to turn to SnapRAID instead. This creates a snapshot of parity for your data disks, and it is an imperfect solution because there's always a delta between when your parity snapshot was taken and reality. This is less of an issue for large, mostly static datasets like media files, but it can be a pretty poor choice for use cases with large amounts of churn like application data or databases. Stuff like your Plex metadata, for example, would be a poor choice for SnapRAID. And finally is Docker. Now, Docker probably doesn't need much introduction at this point if you're already into any kind of self-hosting, but just in case you're not familiar, Docker is a way to run applications in what are known as containers. Containers are self-contained little boxes of code, happy little accidents of code, that will wrap up everything an app needs to run, and it just runs. Using a few lines of Docker Compose configuration, we can deploy any application without needing to have any knowledge of how the underlying application itself works under the covers. And in fact, in the last decade or so, Docker has become the standard packaging format for self-hosting. So let's dive a little deeper now into each of these three pillars. Now that we understand what we're trying to build, let's examine the core technologies that make this possible. We'll start with mergerfs, which solves our first major challenge: how to combine multiple drives into a single, easy-to-use storage pool. Now, mergerfs takes just a bunch of drives, like these 5 on the table here. So this is sometimes referred to as a JBOD, or just a bunch of drives, and it makes them appear as a single drive. It's tempting to call this merging an array, but given there's no fault tolerance or striping of any kind, let's just stick with a merging, shall we? I mean, crows have a murder, why can't hard drives have a merging? Each drive that mergerfs merges typically has its own individually readable file system. This means you can pull a disk from your server and put it into another one and read the contents immediately. So if you want to do offsite backups, you take your hard drive physically out of your server and go and put it into another one at another house, and it will just be read. There's no syncing, there's no rebuild time, no resilvering. Each disk is just a disk. Now, this actually speaks a little bit to what mergerfs is doing behind the scenes. It doesn't really actually care too terribly much about the underlying storage at all. It works at the file layer. So if you give mergerfs a file system, XFS, ext4, btrfs, and yes, even ZFS, it will merge them together into one merging. Disks can be included that already have data on them, and mergerfs will pick them up and their contents immediately. So let's look again at our requirements and see where mergerfs fits in. We want to be able to group multiple drives together under one mount point. I don't want any data striping, and I want each disk to be individually readable. And I need it to support mismatched drive sizes. This one is the killer feature for mergerfs. Take any drive of any size and throw it into your mergerfs configuration, and it will be merged immediately. Unraid, I should note, is also capable of this to a degree, but it's not as flexible because you have to set your config kind of in stone, and then you can't start and stop the array with a drive missing. It's just not as flexible. It's the only other solution in this space, though, that supports individually mountable drives with mismatched physical sizing. Because of this flexibility, you are not locked into the disks you buy on day one. This solution can grow with you very easily. So let me give you an example. Each year on Black Friday, I typically buy 1 or 2 hard drives, depending on the sales that are going on, and I tend to target the $200 to $250 range. With mergerfs, all you need to do is format the disk, add a small entry into your fstab file, and suddenly your storage pool instantly grows by 18 terabytes. No rebuilding required, just instant storage. Over the last 5 years or so, that's meant that my average disk size has grown from about 10 terabytes per disk to now 18 terabytes per disk. So let's suppose you have 5 disks in your system. That also means that no disk in your system will ever be more than 5 years old because you're always rotating 1 or 2 disks a year. And there's always a project waiting for those old drives too. Maybe you can use them to create an offsite backup using something like zfs.rent perhaps. Now, this flexibility in every aspect is why I truthfully think that despite the many advantages of ZFS, it's a poor choice for those of us building media servers. And no, RAID-Z expansion is not going to fix this. I will link to an oldie but a goodie blog post in the description down below talking about the hidden cost of ZFS if you want to know more about what I mean here. There is a place for ZFS in this system, but it's just not the primary storage medium that we're going to use. And we'll get onto ZFS a little bit later. And, by the way, if that scares you off, don't let it, because the use of ZFS here is 100% optional. As disk sizes have exploded over the last decade, the need for tons and tons of them has diminished significantly in a single box, especially when we consider things like H.265 and the AV1 video codecs. I mean, in the old days, to get to 100 terabytes, for example, that often required 20 plus drives. I remember seeing people in the old days on the Unraid forums posting things about like Norco 4224s and like massive disk shelves that needed a small data center in your basement. And that's a lot of noise, that's a lot of heat and a lot of cost, not just in terms of buying 20 plus drives, but electricity and all the rest of it. But nowadays, 100 terabytes is pretty easily achieved with just 5 20 terabyte disks, and a 5-bay system can be built and deployed really easily under a desk without requiring aforementioned basement data center. And again, this is all about flexibility. mergerfs has meant that as drive sizes have increased over the last decade or so, it's been pretty trivial for me to keep up with the latest drive size changes and buy disks, which are going to be your primary expense when building a server, when they go on sale. So you might be wondering, what's the performance impact of using mergerfs? This all sounds too good to be true. And in my testing, the answer has been pretty minimal. Since there's no striping involved, you'll get the native performance of each individual drive, and that usually means these are easily capable of saturating a gigabit network link. And in most cases, the physical write speeds of the drives themselves will be the limit. So these older drives, this is a 4 terabyte drive here. I find that these older red drives, they typically write in the 130, 40 megabits a second range, whereas the newer ones, like the 16 terabyte at the front there, or is it a 10? Whatever. The newer drives can write in the sort of 200-ish range, and mergerfs can handle that no problem. So far, mergerfs has given us the flexibility to combine drives of any size into a single pool. But there's one critical piece missing. What happens when one of these drives inevitably fails? Well, this is where SnapRAID enters the picture, and this provides the data protection layer that mergerfs itself doesn't include out of the box. Now, while mergerfs handles the organization of our files across multiple disks, SnapRAID works behind the scenes to create recovery information that can protect those files from both drive failures and silent data corruption. These two technologies complement each other perfectly: mergerfs for storage flexibility and SnapRAID for data protection. It follows the old Unix philosophy of just do one thing and do it well. Now, recall with mergerfs that it provides absolutely no fault tolerance, as I just said. If a disk in that merging fails, the data is gone. This may or may not be a problem depending on how you sourced the data in question. You know what I mean. I've left my eye patch over there. SnapRAID is a free and open source project licensed under the GPL v3, which calculates parity information for disk arrays, and it can protect against up to 6 failures all at once. It essentially takes JBOD and provides a cohesive glue, I suppose, for protecting them against drive failure and bit rot. It's primarily targeted at media center users with lots of big files that rarely change. Now, SnapRAID supports mismatched drive sizes just the same as mergerfs does, although one caveat is that the parity drive must be as large or larger than the largest data disk. This is very similar to Unraid if you're familiar with that. Now, the name SnapRAID comes from the fact that it isn't really RAID at all, it's actually a snapshot RAID. No striping occurs, and parity information is devoted to an entire dedicated parity disk. This implementation is a major difference from Unraid or traditional RAID like Medadum or ZFS, all of which calculate parity in real time. So let's take a look and see which of our requirements SnapRAID has checked off. We need to provide a fault tolerance to protect against the inevitable hard drive failure. I want checksums for files to guard against bit rot. I need to support hard drives of differing and mismatched sizes, and each drive should have its own separately readable file system with no striping of data. SnapRAID helps us meet each of these criteria, and when it's combined with mergerfs, it enables each drive to remain individually formatted, no striping, whilst still having some kind of fault tolerance. Data integrity is checked for against bit rot using 128-bit checksumming, which enables the silent fixing of these errors in case there has been any bit rot whilst you weren't paying attention. Furthermore, any files changed since the last sync can be restored on a file-by-file basis, allowing for quite a sophisticated backup solution at the file level. I should note an important caveat there that any file since the last sync, so your snapshots aren't versioned or anything like that, you get one snapshot and it was the last one. So if you're looking to recover a file from a month ago, this won't help you. But if you're looking to rebuild the contents of a failed drive, then that's exactly what SnapRAID is for. SnapRAID will also work on already populated data drives, which is a big win over traditional RAID. Again, it allows only the drives in use to be spun up, unlike RAID, which requires all of the drives to be spinning to access a file on just one drive. I'll put a link in the description to a section of perfectmediaserver.com discussing, is SnapRAID right for me? And the answer is probably maybe. Kind of depends on your use case. As I've said, SnapRAID was designed with large, mostly static datasets in mind, like media collections, and we are building a media server here, right? A common use case is a media or home file server. Let's say you have a 2 terabyte collection of movies and a 2 terabyte collection of TV shows. How often does that content change? Well, not very is probably the answer to that. Like, you'll acquire a show and then it will just sit on your disks for the next 10 years until you get bored and delete it one Sunday afternoon. So does it therefore make sense to require a real-time parity calculation and pay the penalty any time you write to your merging? I nearly said array, but I'm going to call it a merging. Does it make sense to pay that parity write calculation tax almost like an unraid would give you, or just run that computation once daily at a quiet time when you're not actually using the server? So here's an example. You acquire a file and save it to disk, and it's called bestmovieever.mkv. That file sits on disk and is immediately available to Jellyfin or Plex or whatever you want to use for playback. But the file remains unprotected on disk until you run the SnapRAID parity sync. This means that if in between your acquisition of said file and the parity sync, if you were to experience a drive failure for some reason, that file would be lost or unrecoverable. It's simple to run a manual parity sync if that file's really important to you just by running SnapRAID sync. But that window of time it's really important you understand that just that window of time is often just a few hours, and depending on how you acquired said file, it really does it matter? I've actually been running without SnapRAID on my server at all for a good 2 or 3 years at this point, and I haven't so far experienced any issues, but your mileage may vary with that. So I include SnapRAID here because I think it's important that we have at least feature parity with the commercial offerings like Unraid, and I kind of don't want to bring ZFS and TrueNAS and all that kind of stuff into the conversation too much because they're aimed at totally different use cases in my mind. Like SnapRAID, for example, is incredibly badly suited to high turnover applications such as databases or app data, stuff like your Plex metadata in a SnapRAID backed array of disks it would perform horribly. Tens of thousands of tiny little files. Each of those have to be opened and closed and transacted through the parity system. It's just not what SnapRAID is designed for. And if this is your use case, you should probably look at a real-time parity-based solution, like running a ZFS mirror, for example, and we'll get onto all that stuff later on in the video series. But for now, if you can cope with this risk window and have a largely static dataset, SnapRAID is probably the right choice for you. There are several projects available to automate this parity sync daily. You can just throw it in a cron job if you want to, but there are some more sophisticated ways to do it, which again, we'll dive into later in the video series. SnapRAID, by the way, does offer a drive pooling feature that on the face of it looks like it makes mergerfs superfluous. However, the pooling feature by SnapRAID creates a read-only virtual view of the files in your array using symbolic links, and we want to be able to read and write to this array with various different applications, and the SnapRAID pooling option, it can be useful as a hobby project, but it's not suitable as the primary mount point for our system. Now that we've established how to store and protect our data with mergerfs and SnapRAID, let's talk about how we're going to actually use that data storage. This is where Docker comes in, and it provides a simple approach to deploying and managing the applications that will bring your media server to life. Back in 2016, when I wrote the original Perfect Media Server article over at linuxserver.io, Docker was barely 1.0. It was brand new. Fast forward several years, And containerization has cemented itself as a major player in the industry. In fact, 10 years ago, you were pretty crazy if you ran containers in production. Now you're pretty crazy if you don't. For those of us looking to build a media server though, containers offer a uniquely brilliant way to run applications. They divorce the running application from its data whilst making managing their persistent data and configuration really straightforward and simple. So why should I use containers? Well, we'll come on to what a container is shortly, but first, let's discuss why you might want to consider using them at all. My light bulb moment with Docker came a few years ago after I'd reinstalled my server OS. I'd gotten everything working pretty much the way I wanted it, but for some reason, an update came along and broke everything. However, this time I was using Docker for my applications to store the data for those applications in volumes, bind mount volumes. And I'd kept a text file with each of the Docker run commands I'd used to create those containers in the first place. Remember, this was pre-Docker Compose. This really was a long time ago. What normally followed reinstallation was a lengthy, often multi-day process of getting things just back to where they were, of resetting up a whole bunch of apps. This time though, things were different. I'd copied each Docker run command and I was back up and running within about 10 minutes. I was done. That was it. The game changed for me that day. This is because the configuration data for the applications was stored in a separate location in a volume, rather than being lost when I'd reloaded the server. Containers also provide a number of other benefits. These range from portability to standardization to security to, in my case, employability. Yes, a lot of the skills I've learned building a, on the face of it, poxy little media server have led to me having a career in DevOps and networking and all this kind of stuff. Do not underestimate the value of having a server at home that you can hack on and break and learn with. Another oldie but a goodie resource is a talk by James Bottomley from FOSDEM in 2016 that really cemented my understanding of containers. I'll put a link to it in the description down below. It's good stuff. Docker Compose touts itself as a tool for managing and deploying multi-container applications. However, it excels at managing the application containers most of us will run on our media systems. You can declaratively define the image, the container name, the volumes, the ports, and everything else that make up what is going to be that deployment of that thing, and capture that in a YAML file in a self-documenting system that will save you from that really annoying, how did I do this 6 months ago again question? Be honest, we've all faced that at one time or another. I made a video in the early days of this channel about how I manage my Compose files with Ansible. Now, we haven't touched on Ansible yet because I don't want to scare people away, but it's something I use on the daily for doing a lot of my system configuration via automation. And don't worry, I will avoid it for as long as possible just to try and keep things as simple as possible. We'll probably come on to that in part, I don't know, 3 in this video series. I'm not entirely sure yet, but I will stay away from the Ansible Kool-Aid as long as I possibly can. So you can head over to perfectmediaserver.com to take a look at all of the available documentation I've written over the years. But this brings us to the end of part 1 of our Perfect Media Server journey. If you found this helpful, please consider subscribing to catch parts 2, 3, and 4 in this series, and drop your questions about mergerfs, SnapRAID, or Docker in the comments down below. I will respond to and address as many as I can as I make this series. This is a real-time thing. Like, part 2 isn't filmed yet, so if you ask a question in the next week or 2, I will do my best to address it moving forward. Now, thank you so much for watching, and I'll see you in part 2. I've been Alex from KTZ Systems.